Hey there everybody, and welcome to the next video on SIR models. In the previous video I gave sort of a global overview of the models, but I did no mathematics. And this video will do the math. So we're going to build the model mathematically, and in particular, as I mentioned in the last video, there are three populations of interest in any sort of epidemic setting. Each population has its own differential equation. So I'm going to build those three equations for you and then talk about how those three equations model the spread of disease. We're going to start, though, by reviewing the basics of math modeling, just to put ourselves back in that headspace. We did this back in Chapter 2, but it's worth doing a reset here just for contextual purposes. So, mathematical modeling, what is that? All of you know this, but it's worth restating. You're building a mathematical tool, often an equation, or for us now a system of differential equations, that allows you to make predictions. That's why you build a model, so you have some estimate of what's going to happen in the future. Any math modeling problem has 4 steps. First, you state your assumptions, and you do this so that you can build your model. Stating your assumptions in physics, the classic example, right, is ignoring air resistance, right? That's an assumption you make, and that assumption allows you to build a model. So anyway, you just say up front what you're assuming. Then you solve your model in step 2, and it's worth pointing out that the solution part, the really like mathy math part, right, is purely mathematical, and that part doesn't care at all about what the physical context was. Okay, so step 1 is not a purely mathematical step. You're making assumptions about a physical system. Step 2, though, you do the math. Step 3, you put that math back into its physical context. You interpret what you just did in the physical setting you're interested in. And then finally, step 4, you ask yourself, is this model any good? Is it just spewing out nonsense? Or is it telling me something that might actually be true? So in practice, you would always reevaluate your model after you've made predictions with it, and you may have to calibrate it to new data. So back in Chapter 2, we did all 3 of these things. We didn't do any of 4. But in this section now, we actually are going to discuss some data calibration, calibrating your model to data, checking your data or your model after the fact, and reevaluating it. So anyway, this is the complete sort of math modeling process. In an epidemic setting, I just want to start by talking about the variables of interest. At any given time during an epidemic of the kind of disease we talked about last time, things like the cold, flu, whooping cough, etc. Oh, not whopping cough. For some reason that's funnier sounding than whooping. Anyway, we're interested in the following 3 variables or populations. We talked about this in the last video, but let's set it up again. The number of people who are currently infected with the disease, although technically when I say infected or when the literature says infected, what they actually mean is infectious. So capable of infecting others. With some diseases, you can have the disease in your system and thereby technically be infected, but not be able to spread it yet. Okay, so there are models that make that distinction and care about that distinction, but for now we're going to just use these terms sort of interchangeably, even though we know they're not exactly synonymous. Okay, the number of people who can no longer be infected, either because they have had the disease and are now immune, or because they have died. Okay, so the second group of people, it seems weird to group dead people in with recovered people, but that's mainly just to keep the model sort of simpler and streamline it. And I mean, obviously it's terrible to have died, but at the very least, if you have died, you are immune from the disease. You can no longer get it. So anyway, this population 2 is just the people who can no longer get the disease. Finally, the number of people who could still get the disease, the number of susceptibles. Those are the variables that we care about. Underlying all of this is an independent variable, time, which for us will be measured in days. These populations, right, they depend on time. On a given day, you'll have a certain number of each of the 3 populations. We're going to use this notation for the set of independent variables modeling those 3 populations. Capital S for the raw number of susceptible people, capital I for the number of infecteds, and capital R for the number of recovereds, where again, recovered is a bit of a misnomer that encompasses people who have literally recovered and also those who have died. These are the 3 variables of interest, dependent variables of interest. And now you can see why this is called an SIR model, right? Susceptible, infected, recovered model. We also, for the sake of graphing purposes, will care about the fractional variables. So if you take the number of susceptibles and divide by the total population, you just get the fraction or percentage, if you like, of the population that is currently susceptible. Same for infected and recovered. So, I mean, there are 6 variables we care about, but in the end, when we get graphs of things, we'll graph these 3 variables. The reason we will care about these 3 is that if you think about a vertical scale, like how long does your y-axis need to be? If you're dealing with percentages, it only has to go from 0 to 1. Whereas if you're just dealing with like the raw numbers, you know, the United States has like 350 million people or whatever, right? So if you wanted to model COVID-19 in the US, your vertical axis could be as long as from 0 to 300 million. So if you deal with fractions, it just keeps the graphs nice and compact. Okay, first questions. If we were in class, I would ask you to think about these. I would ask you to make sketches and put them on the board, and we would talk about them. Anyway, so it's still worth thinking about now. How do you think the graphs of these 3 populations vary with time? Sketch. What do these things look like, you know? So make some sketches now, and we will verify them in the next video. So in the next video, we will actually produce graphs. We'll have the computer produce graphs showing precisely what these 3 curves look like, given a particular disease and a particular model of it. Okay, so now on to building the model. The first thing always, right, is to state your assumptions. These assumptions drive the eventual equations you build. Assumption 1 is that the total population during the course of the outbreak doesn't change. The total population is a constant n. So what does that mean? That basically means that I'm ignoring births and ignoring things like immigration. And by the way, I'm not ignoring the dead, right? If you die, you're actually still part of the model because you're part of the recovered group. So I'm not ignoring deaths, I'm just ignoring births. And so, of course, that's not reasonable for any sort of long-term predictive model. But generally speaking, we're only looking at a matter of months, perhaps a year with these models. Like the flu, it lasts for what, 2-3 months. So it's okay in general to ignore things like births and immigration on such small little time horizons. Okay, the second assumption is that no one is added to the susceptible group. That's sort of an outgrowth of the no births thing, right? Because in general, we as a species produce new susceptibles all the time through births, but we're, again, ignoring that. So here's sort of like a flow diagram for the process for the populations. So susceptibles can become infecteds, and then infecteds become recovereds. So the only way an individual leaves a susceptible group is by becoming infected, right? So again, that's just part of this flow diagram here. So a susceptible at the beginning of an outbreak, they either stay susceptible because they never get the disease, or they get the disease and become infected, and then eventually make it to the recovered group. Okay, let's just start drilling it down on some of the math here. So far these assumptions are particularly mathematical. Here's our first sort of mathematical assumption. We'll assume that an infected person stays infected on average for k days, meaning that on a given day during the course of the outbreak, approximately 1/k of the infected group recovers. So just for example, if k equals 4, that means that you are sick for 4 days. Well, if everybody is sick on average for 4 days, then on average about a quarter of the infected population recovers on a given day. And again, it's still worth reminding ourselves that infected really does mean infectious, right? Capable of spreading the disease. So even after you can no longer spread the flu, say, you can still die from it, right? Because you've moved on to, say, pneumonia or something, whatever. Okay, the fifth and last assumption deals with sort of how contagious the disease is. So no assumption yet has addressed that some diseases are more contagious than others, right? Our fifth assumption addresses contagiousness, among other things. So finally, we assume that the number of susceptibles on a given day depends on 3 things. Depends on the number of people in the susceptible group. So this variable S depends on itself on some level, right? Because the fewer susceptibles there are, perhaps the less likely you are to leave the susceptible group. If there's a small number of susceptibles, because there's a ton of recovered people, then you're not likely to run into an infected person. So anyway, the number of susceptibles depends on how many susceptibles there are. Also depends on the number of infected, right? If you are susceptible, the more infected people there are, the more likely you are to become infected yourself. So the number of people susceptible today depends on how many infecteds there are. And finally, of course, the number of susceptibles will depend on the amount of contact between the two groups. So in a society in which lots and lots of people are infected, millions of people are infected, however, there's no contact between infecteds and susceptibles, then that doesn't matter, right? For susceptibles. Doesn't matter how many infecteds there are if there's no contact. Okay, so with that being said, let's start thinking about building a sort of assumption about contagiousness. So we'll let tau be the probability that a susceptible person will become infected given a contact between a susceptible and an infected. Okay, so there's a lot actually packed into this word contact. What do you mean, contact between susceptible and infected? And basically what I mean is a contact is any contact. It feels bad to self-reference and the definition, but any sort of contact that's like sufficient to spread the disease. So if I have COVID-19 and I shake your hand, that's a contact. If I have the measles and I sneeze in a room and you come in that room 3 hours later, that's a contact because there'll still be measles particles in the air. If I cough in your face, that's a contact, whatever. Anyway, so given a contact, there's some probability that you'll become infected if you're susceptible. Okay, so if I cough in your face and I have COVID-19, you are not guaranteed to become infected, right? There's always some probability at play. So tau is basically that probability, sometimes called the transmissibility. Okay, so before I move on, let me just bring up this Washington Post article. Okay, so hopefully you all have read this before diving into this. Let me go down to these simulations that are really nice. Okay, so you should imagine, so in this picture I have blues are susceptible, oranges are infected. Imagine the population doing this, right? Just kind of bouncing around whatever, like little particles. And so, of course, in general, populations don't act like this. They're not sort of like random walking particles. However, something like this actually has been shown to be a pretty good approximation of, in aggregate, how society behaves. So in any society, there are some of these little balls that just like what's happening now. Some of them just stay in place, right? So there's some people that just like sit at home all day, no matter what's happening outside, right? There are other people, though, that just like jet all over the place, you know? Some people are like scurrying through this diagram super, super fast. So on average, it kind of goes like this. People are just kind of bouncing around on average. One thing also to notice about the simulation, whenever you see an orange ball or dot hit a blue dot, it always turns orange. Okay, anytime an orange contacts a blue, let me just, refresh this so you can see that. I mean, I'm sure you can see it on your own computer, right? But notice, anytime an orange, right? That orange there. Let's track it. Boom, it hits. That's an orange now, right? So in this sort of Washington Post simulation, tau is 100%. They are assuming that anytime a infected person contacts a susceptible person, that susceptible becomes sick. So that's not particularly realistic, right? I mean, even with something like measles, which is super, super contagious, there's some non-zero probability I won't get sick if you cough on me. Okay, so anyway, so you should imagine the population going like that. People bouncing around, right? And anytime you get sort of a blue dot hitting an orange dot, there's some probability, tau, that the blue becomes orange. Suppose that each infected individual has an average of C contacts per day with other people in the population. So I'm infected, and maybe like 5 times per day I cough on somebody, right? Well, those 5 coughs I do, right? If I cough on 5 people, I'm not necessarily going to generate 5 new sick people. Because, first of all, there's a probability involved, right? Also, though, maybe I coughed on 5 other sick people. Or maybe I coughed on 5 recovered people. Whatever, right? So anyway, the average number of contacts a day that I will have with susceptibles, though, is this. I have my C contacts per day times the percentage of people that are susceptible. That's sort of the number of contacts on average I'll have with susceptibles if I'm sick. Okay, so just to make that concrete, suppose that tau is 1/3, B is 6, and the percentage of people today that are susceptible is half. So half the population could still get the disease. So suppose I'm infected. What that means is that I'm going to like cough on 6 people today, or sneeze around 6 people today, or whatever, right? Shake 6 people's hands. Because half of the population is susceptible, on average, 3 of those contacts will be with susceptible people. Okay, so if I have 6 total contacts, assuming all these assumptions here, right? If I have 6 total contacts, about 3 of those will be with susceptibles. And then, since the probability of transmission is 1/3, I do 3 times 1/3 and get just 1 new infected person. Okay, so anyway, if these are the parameters assumed now, then on a given day, 6 contacts will turn into 1 new infected person. So on a given day, how many new infected individuals will be generated? Well, as this example shows, you just multiply down the line. So you take B, multiply by 1/2, take that result, multiply by 1/3. Okay, so in the end, each infected individual is expected to generate tau times C times S of t, new infecteds on a given day. And B here I'm just defining as tau times C. B is what shows up in the literature, sometimes called the effective contact rate. Okay, so all that to say, on a given day, if I am sick, on average, how many new sick people will I generate on that day? Again, it's just this multiplication. Probability of transmission, number of contacts I have, times the fraction of people that could actually get the disease. So the takeaway from this slide is this. On a given day, 1 sick person generates that many new sick people, according to our assumptions. Okay, so just a quick note on B here. One way of thinking about B is the number of contacts by an infected person per day that's sufficient to spread the disease. So again, think about coughing on people, right? Not guaranteed to spread the disease, but sufficient to. It's possible to. So if you see this in the homework, right, each infected person has 1 contact sufficient every 2 days. That's 1 per 2 days, right? 1 per 2 is 0.5. So just keep that in mind when you do the homework. Okay, so now let's build some differential equations. Here is an equation for susceptibles. So I claim this. The rate of change of the susceptible population is negative B times the percentage of susceptibles there are times the number of infecteds. Why is that? Why would that be true? In particular, why negative? Why is there a capital I there? And then given this? Why can we write down this DE for their percentage? And one thing to note real quick is that just like back in chapter 2, you guys remember liking this? We all liked this, right? The rate of change of a population is the rate in minus the rate out, right? So on a given day, right, this is per day, on a given day, how many susceptibles are coming in? The answer is 0, right? We're assuming no bursts, no immigrations, right? How many susceptibles are leaving? That's for you to think about, right? On a given day, how many susceptibles are leaving? Well, we just said, or I just said, that each infected individual generates this many new infecteds on a given day. So each infected person generates that many people that are now flowing from S to I. So if each infected does that, then scaling by the total number of infecteds on a given day gives you now, this is just the total number of new infecteds today on a given day. And all those people are leaving the susceptible group. Leaving means negative, right? So the population of susceptibles can only go down. We don't create any new susceptibles. Anyway, so if this is true, you can divide this equation by capital N by the total population. If you divide the left-hand side by capital N, you get now a lowercase s. Divide the right-hand side by capital I, you get a lowercase I. The recovered equation. Why is this true? So think about this for a minute. When I say think about it, you can always pause and think about it, right? But again, any DE here can just be written as rate in minus rate out. On a given day, how many people are being recovered, right? How many people are recovering on a given day? Well, we already said, right, on a given day, this many people recover, right? 1 over K's worth of the infected population recovers. So on a given day, this many people flow into the recovered population. So again, if K is 4, that was our example, then 1/4 of the sick population becomes well on a given day. So there's just flow, straight from I into R. Well, if this is true, you can again divide by capital N to get the percentages. The infected equation. Here's an equation for the infected population, and you get this from here, okay? So you should think about, why is this true? And then why is this true? And what assumption are we using here? Why is it that the three derivatives of fractions total 0? And the answer is, I could divide this equation here by capital N to get lowercase s, lowercase I, lowercase r, 1 over here, right? And then if you take derivatives of both sides, you just get these three derivatives added together. The derivative of 1, though, is 0. So we actually get this nice little equation because the total population is constant. Now, if you want di dt, what do? You substitute in for ds dt, right? There he is. Oh, sorry. So you don't just substitute straight in, right? You substitute in and then subtract over, right? So di dt is what? It's ds, negative ds dt minus dr dt. So that's why the signs are swapped. Anyway, this should be recognizable to you, right? That's basically ds dt. It's just ds dt was negative that, right? Why was that negative there? Because it was an outflow. But where is that outflow going? It's going to the infected population, so now it's positive. This you should recognize from the previous slide, right? This was flowing into the infected population. Where was it flowing from? Flowing from the infecteds. So it's negative for the infecteds. So all that to say, we have these three differential equations now. S prime equals negative bsi, I prime equals bsi minus I over k, R prime equals I over k, where b and k are constants that depend on the particular disease and how the population is behaving, and environmental factors perhaps, whatever. Okay, if you want to solve this model though, right, if you have a system of DEs and you want an exact particular solution, you can't just have the DEs, you also need initial conditions. If all you have are DEs, you're going to get these degrees of freedom constants floating around in your solution. Well, we have three initial conditions, right? There's some initial population of susceptibles, which at first anyway, we're going to assume is basically the whole population. There's some initial population of infecteds, which we're going to assume is small, so basically 0, but not equal to 0. And then again, at first, we're going to assume nobody's recovered, so nobody has immunity. Okay, so here are sort of the three initial conditions. And if you want the fractional ones, then the initial percentage of people who are susceptible is basically 1. The initial percentage of infecteds is basically 0, but not 0, small though. And then the percentage of people who are immune is 0. So here is, in all of its glory, the complete SIR model in its fractional form. The three differential equations, the three initial conditions. So let me just conclude this video by pointing out there are 5 constant parameters in the model, which are listed below. There's this B, effective recovery rate, a K, which is how long the disease lasts in a given individual, and then the 3 initial condition numbers. Which of these parameters can public health officials hope to control? Let's just go through them one by one. Can they control K? I mean, not really. In general, there might be some drugs that might help the flu infectiousness rate drop by a day or something, but generally speaking, you can't really cut down on the length of infectiousness period. Also, I of 0 for our models would generally be super, super tiny, and it just assumes that on a plane, a COVID-19 patient flew from New York City to Kansas City, whatever, right? So generally speaking, these two constants you can't really hope to control. However, what about something like B? B, among other things, depends on the amount of contact between infecteds and susceptibles. So if you do things like quarantine people, social distance, wash your hands a lot, and so on, right? B can actually be made smaller than it otherwise would be. You can control B through these sort of social control measures, right? What about the initial amount of people, or the initial percentage of people who are immune? Well, if a vaccine exists, then you can try to get people to use it. And the more people who are vaccinated, the larger this number becomes, and that's good. Right? The larger this number is, the more people who are immune. And you get herd immunity kicking in, and it's hard for an epidemic to occur, right? So in other words, when you make R of 0 high, you can make the number of susceptible people small. right? You can sort of like wall them off from any possible infecteds. So, okay, so if you're a public health official, there are sort of two avenues for you to try to control these models. You can create a vaccine and get people to use it. That would control this parameter. You can also try to get people to wash their hands and like stay in their houses. That controls this parameter. Okay, so in the next video, I want to pick up with an actual example that we will solve from start to finish, or I guess to be more precise, the computer will solve. Hopefully, this has given you sort of a solid introduction to the three differential equations with their three initial conditions.